Hey guys, today we're going to be going over the solutions for round 666. Um, in terms of the contest itself, went relatively well, given that I had a horrible night of sleep. I'm actually surprised that I gained rating at all, so that was good, I guess. And it was kind of a rough round, but some of the problems were at least enjoyable. So before I get into that, I kind of want to talk about, remember in the last video, we had a poll about, where is this? On the last video, we had a poll about, I'm very organized about doing things. Sorry, I should have pulled this up beforehand. But we had a poll that was basically asking, since school was going to start tomorrow, if I should start doing like virtual screencasts and stuff. For say, for example, I missed the Act Coda round because of Code Chef, so it would depend. So this would depend on that, whether you want to see me do that virtually or just have the solutions for it, which I should get around to doing. And basically, it wasn't even, but it also wasn't that one-sided. Like there were like 58% on one side, 42% on the other. So I've been thinking about ways to compromise. And there was this nice comment on my lunchtime video that I think is a really good idea. Doing like, instead of doing the contest that I would normally do, maybe doing some more advanced contests that happened further in the past. For example, like at Coda regular contests or stuff like that. So extending that idea, what I'm thinking is maybe we could have it so some sort of system where you guys can suggest like contests to me that you want to see, for example. And maybe if it works out, I can try and live stream those, and then we will you'll be able to like interact with me and maybe ask questions about what's happening or something. I don't know, I kind of like that idea. If you guys also do, cool, I guess discuss in the comments. I'll see what you guys think about that. And yeah, that's my plan, I guess. I'll also continue doing the official rounds. Because of school, I'm probably going to skip this upcoming Div 1, but I can do either virtuals or solutions for all of these upcoming rounds later on. There's some on ActCoder. Can expect some cool Code Chef editorials soon enough. That'll be a nice surprise. And yeah, there'll be good stuff in the future. So for now, let's go over these solutions. So again, this is round 666, or 666. I'll go over all of the Div 2 solutions, since I don't know how to do the Div 1 only problems. And without further ado, let's begin. So this is A, and basically here's the problem. You're given a list of strings. Yeah, you're given a list of strings, specifically given a list of n strings, and let's say, for example, the sample, CAA, CBB. And what you can do is, you can delete a character from a string and put it like anywhere else, in any other position. You can even put it in the same string. So you can rearrange the order of the characters in any way you want. And you can do this operation as many times as you want. You want to find out, is it possible to do this operation some number of times such that in the end all strings are equal? Okay, let's define a case. Well, actually, so first of all, because we can change the order however we want, the order can't possibly matter in the final answer. And so the order of the characters doesn't matter. What does matter is the number of each character we have. And the reason for this is because, well, we can change the order however we want, but the number of each character is fixed. So in this example, we have 2 times A. That's a terrible A. We have 2 B's and 2 C's. And the handwriting is inconsistent, which is even better. And what can we do with this? Well, something cool about this is that in this, for example, in this case, we can make the string CCBBAA. Okay, now here's the claim. Because order doesn't matter, and all we care about is the counts and the number of strings, like both of them have to be used in the answer, right? So let's use both of them. What if we construct a string where we say, first we'll place, like we'll pick one character and then place that character down in all of the strings we have. So right now we have 2 possible slots for strings. So we're going to take the 2 A's and we're going to put them at the beginning. So now we have 0 A's. Then we're going to take the 2 B's and put them at the beginning. Now we have 0 B's. Now we'll take the 2 C's and put them at the, or not the beginning, like the end of the string, sorry. And now we have the same strings. So even if we, for example, had 4 times 4 C's, then we could just put 2 C's down at the end of everything. And this process is going to work. However, it's only going to work if we can, in fact, put a character down in each string every time. And all that means is that we have to either have some number greater than n, we have to have exactly n, or we have to have 0. And if we have a number greater than n, then we have to subtract n from it, and eventually we have to get to a point where we get to n, or 0, either n or 0. So basically we have to subtract n a bunch of times until we get 0. That means the number of each character has to be divisible by n for this process to work. So if the number of every character is divisible by n, this also includes characters that aren't there. For example, we have 0 F's in our strings. However, 0 is still divisible by 2, so that's fine. And because of the process I just showed you, this will always work. If we have the condition that all strings are divisible, all counts of characters are divisible by n, we can do it. Now, the harder part is showing that it's necessary for this to be true. Because we've shown that if it's true, we can make an answer. But now we need to show that it's impossible to make an answer if it's not true. And here's why. Let's do the same process. We have 2 strings, and let's say we had 3 F's. Clearly 3 is not divisible by 2, right? So that means one string is going to have a different number of F's than the other one. For example, let's say this has 2 and this has 1. Then there's no way this can be equal. In our final construction, every string has to have the same number of F's. So for example, if we had 4 strings, then that also wouldn't work because we would have to have 2 strings that are different. So basically that shows why it's also necessary for every string to have the count of every character to be divisible by n. However, it turns out that's the only condition. So you just need to count the characters, all of them, in each string, because you can reorder them any way you want. It doesn't matter where they are. And you just need to check if all of the counts of those characters are divisible by n. N being the number of strings you have to create in the end. Yeah, that's a relatively simple idea. Kind of possibly hard to come up with, but it's kind of nice. Okay, this is B. And I imagine it gave a lot of people a lot of trouble in terms of implementation. So you're given an array. Let's say 1, 3, and 2. You can do 2 things. At the beginning, you can reorder the array however you want. So for example, let's say you can change the order of the elements. So let's say I change it to this. Then you're going to pick some number, and you're going to pick some number r. So then, with this number r, you want to either decrease or increase each element some number of times, each time being a single each increment or decrement being a single operation. And you want to use the minimum number of operations to make the sequence into something special. Let's say the definition in the statement is that you want the sequence to be of a form like this. So it's the first element is 1, the second element is r, the third element is r squared, the fourth element is r cubed, the fifth element is r to the fourth, and etc. Right, so basically, for example, in this sample, let's say we had r equals 4. Then this would be 1, this would be 4, this would be 4 squared equals 16. Then we need to convert 3, 1, and 2 to these numbers. So this we need to decrease by 2, which means we use 2 operations. This we need to increase by 3, and this we need to increase by 14. So in total we use 19 operations. But let's say we pick r equals 2. Then we have 1, 2, and 4. So we have 3, 1, and 2 here. So we decrease by 2, increase by 1, increase by 2, and clearly this is better. We only used 5 operations. So there are many different things you can do, and you have to find the minimum number of operations it takes to make this happen. Okay, now how do we do this? First of all, actually, this kind of relies on 2 different observations, both of which make for relatively simple implementation. However, it's hard to think of these, or it can be hard to think of these. So first of all, the optimal reordering is to sort the array. We want the array to be in non-decreasing order. Every element is either greater than or equal to the element before it. The reason for this is as follows. Let's think about the sequence 1, r, r squared, and etc. This sequence is also sorted because either r is 1, in which case we just have a bunch of 1s, and a bunch of 1s is sorted, or we have some number bigger than 1. So we have 2. 2 is bigger than 1. Then 2 times 2 is also bigger than 1. 2 times 2 times 2 is bigger than 1, and etc. So the final sequence we want is also sorted, which means let's say we swapped 2 elements. So we made this sequence 1, 3, and 2. But compare it to the sequence 1, 2, and 3. The only difference here is that this is 1 less and this is 1 greater. However, or let's say the only difference from the sorted sequence that this purple one has is that this is 1 greater and this is 1 less. But this number is the smaller one and this number is the bigger one. So when we use this ordering instead of this ordering, either we get farther away from the smaller one or we get farther away from the bigger one, or in this case both. But in the sorted order, we'll always be closer to the smallest and the biggest ones than if we don't sort it. That is definitely not a formal proof, but there's definitely some intuition that goes behind this. And basically, you can show that if you swap, if two elements are they form an inversion, that is, one comes before the other and is also greater than it, then it's optimal to swap them. Because, for example, here you can see that if we made this a 2 and this a 3, then the distance here would be decreased by 1, and the distance here would also be decreased by 1, so it would take 2 fewer operations to get to the final answer. And even if it doesn't reduce the number of operations, it definitely doesn't increase the number, so it can't hurt to sort it no matter what. So now we'll assume the array is sorted, and now we just want to find the optimal value of r. How do we do that? There are many ways you can do this. However, there is an easy way. N is greater than or equal to 3. The array elements are up to 10 to the 9th. So the solution is simple. Try all possible r. I'll let that sink in. Why does that work? Because, well, actually, first let's find a bound on the number of operations we can do. So an obvious candidate for r is 1. r equals 1. Now what happens if we just change all of these elements to 1? Then the cost for doing this is the sum of all AI subtracted by 1, since you have to decrease all of these elements until they become 1. So it's the sum of AI minus 1 up to 10 to the 9th, right? So this is at most, let's see, it's around like 10 to the 14th. So now let's think about the final sequence. We have 1, for example, n equals 3, we have 1 r and r squared. So let's say we have r equals 10 to the 9th. Then the sequence is 1, 10 to the 9th, and 10 to the 18th. Since our elements are at most 10 to the 9th, obviously 10 to the 18th is way too big. And it's going to be nowhere near the cost. It's going to be nowhere near the upper bound of 10 to the 14th. So we only need to try r that are plausibly going to be less than this bound. And how do we do that? Well, basically, let's say you have some r that makes something like huge. Like, for example, 3 times 10 to the 14th. Right? Now, since this is farther away from 10 to the 9th than like anything else will be, no matter what, this will hit the bound. So, like, I picked 3 arbitrarily, but you can basically use as an upper bound any number that's like reasonably larger than the sum of AI minus 1. So for example, in my code, I use the value 5 times the sum of AI minus 1. And if any value in the sequence of r's, so for example, let's say we have r equals 10 to the 8th, that means r squared equals 10 to the 16th. 10 to the 16th is way bigger than 5 times the sum of AI minus 1, no matter what. So therefore this r is too big, and any bigger r is also too big, so we can stop here. So this is how we cut down the number of r's we can try. Now that's cool. Yeah, so basically we use this as an upper bound, and if any value in this sequence ever exceeds it, then you can stop. Now, there's some implementation messiness we have to handle here. How do we check that, for example, a specific value of r to the k is greater than this value? Let's say, for example, 10 to the 14th. How do we check that? There is an implementation detail we can use here. It's quite simple, actually. Let's just, it's easy to jump to using inbuilt STL functions, like, for example, pow. So you would call pow r to the k, and this would create a double. However, because there's like some precision stuff going on in the background, this isn't always going to work. So what I think the better thing to do is just to essentially manually compute r to the k. So first you create 1, then you create r, then r squared, then r cubed, then r to the 4th, etc. And if any one of these numbers exceeds the limit you have, then it's too big. Now the reason this works is you can always, let's say you've generated up to r cubed, then you can check if the next element is too big without explicitly generating it. For example, we want to check if r cubed times r is greater than m. Let's say m is the limit. So if we generate r cubed times r, we might overflow, but what we can do instead is check, we can just move the r over to the other side. So r cubed is greater than m over r. Now this won't overflow because we know that r cubed doesn't overflow because we already computed it. M over r is less than m, less than or equal to m, so that also won't overflow. So if we just manually compute all the values of r up to r to the k, and then check for overflow this way, then we can see if a value of r is too big. And I will refer to my code here. Essentially, this is exactly what I do. So I iterate up to k, and then you check this condition. If r times v is greater than max, which is the same thing as if r is greater than max over v, then it's too big. Otherwise, continue moving on. And if you never find anything that's too big, then it's not too big, so return false. And therefore, it's not too big. Then I just go over and try all possibilities. So once we're trying a value of r, the way to actually compute the cost it takes is simple. We have, like, for example, 1, 2, 3, and then we've already computed the target value, so we can just do it like this. So for example, let's say r equals 3, then we have 1, 3, 9. Then the distance is just like the absolute value of ai minus r to the I minus 1, I guess. Or I, depending on how you 0 or 1 index. Actually, I'll use 0 indexing, so it's just r to the I. And yeah, then you take the sum over those, and that's the cost to check that particular r value. So that will work. That will find the answer because we're literally trying every single possible feasible value of r. And we're just pruning off the ones that have absolutely no chance of working. Now the harder part, I'm not going to delete this yet actually. The harder part is the complexity. Like, why does this pass? As you can see here, my code, it takes 31 milliseconds. But why is it so good? Because the complexity is very informally O of the number of R's we try times N. Now, how do we compute the number of R's we try? So one cool thing we can say is that, like, let's say N equals 100. Then if we even try R equals 2, then we'll get values up to 2 to the 100 minus 1, or 2 to the 99th. Clearly, 2 to the 99th is greater than 10 to the 14th. So we can say if N is greater than 100, then the number of R's is 1. So for N is greater than 100, and in fact this bound can be lowered a lot, I'm just picking an arbitrarily big number, then the number of R's is 1. In fact, let's go even smarter. Let's say 70, because 2 to the 70th is also very big. You can compute that for yourself if you want. Yeah, 2 to the 70th is very big. So otherwise, N is less than or equal to 70. Specifically avoiding using 69. And now how many R's do we have? What? Basically, the number of R's that we have is, it's the maximal R such that R to the m minus 1 is less than or equal to the sum of ai minus 1. And in fact, we can even use our artificial upper bound, for example, 5 times the sum of ai minus 1. Again, 5 is an arbitrary number, so you can use whatever you want as long as it's bigger than 1, and clearly anything too big will obviously not work. So if we again manipulate the equation, then we have r is less than or, let's take the nth root of both sides, or the n minus 1th root. Then r is less than or equal to the n minus 1th root of 5 times the sum of ai minus 1. Okay, this is very messy, but basically, so the n minus 1th root gets smaller as the n minus 1th root has less and less of an effect as n gets smaller. And in fact, the worst case for this function is square root of the sum when n equals 3. But for n equals 3, the sum is at most 3 times 10 to the 9th, because that's just what it is. So our artificial sum is at most 15 times 10 to the 9th. So that's not really that much. Let's just compute that out actually. Square root 15 times 10 to the 9th is 122,000 times 3. 367,000. This will absolutely pass in a very short amount of time. So this messy thing is the formula for the number of r's we have, and basically it never gets too big. If you're very skeptical about this value, for example, in contests, and you don't want to risk timing out, you can just use a program to actually compute these values and see if any of them are too big. Or you can notice that this function takes effect and is way stronger than the sum, which only increases by 10 to the 9th each time. So you want to minimize m minus 1, and therefore the minimum is at 2. And you can also try something like n is greater than or equal to 70, and it will just work. But again, if you're very skeptical, you can just try and compute these values by yourself, using a program, for example, since this isn't a very complicated formula. And yeah, so this will definitely pass in time. That's about it for B. The idea is relatively simple. You just sort it, then try all possible values of R and make sure they don't get too big. Oh, and you can also do overflow checking by using doubles. I guess this is a possibility. I prefer not to do that because of precision errors, but I mean, whatever works really. Actually, precision shouldn't even be that big of a deal, so it's probably fine to do it with doubles, I guess. And that way you don't have to do weird checks like r cubed is greater than m over r. Instead of just r to the 4th is greater than m. So yeah, that is B. C is cool. I liked it, kind of, except for the sample. So you're given an array of length n, where n is big, up to 100,000, and you can do the following operation. So pick a subarray. This subarray is of length 3. Then what you can do is you can add a multiple of the length of the subarray, in this case 3, to any of the elements. And you can pick a different multiple each time. So I can add 6, which is a multiple of 3. I can add 0 to this, and I can add negative 69 to this one, which is also a multiple of 3. And then the new array will be 7, 3, and negative 67. And of course, the 4 is untouched, so it'll stay 4. And you can do this You can do this operation exactly 3 times. And you have to do it exactly 3 times. And your goal is to make all of the array elements equal to 0. This seems like a daunting task at first because like you have 3 operations. How? Okay, now well, we have to do something. So let's think about the last operation we do. In the last operation, for whatever segment we choose, let's say for example we choose this segment of length 2, we have to have it set up in the previous operation so that everything is a multiple of 2, for example. But if we can do it for this array, if we can do it for this subarray of length 2, we might as well do it for the whole array. So we can now assume that the final operation is on the full array, and now we have to make everything be a multiple of n. So we have 2 operations left to do that. How exactly do we do this? So basically every element has a value ai. So now let's pick first of all, let's say if we pick something of length 1, then we can just we can do anything we want to it because everything is a multiple of 1. So we'll just, for example, make this 0, and then we'll be done with that one. 0 also happens to be a multiple of n, so we'll be happy. Specifically, we'll subtract 1 and then make it 0. Now, if we do an operation with any other value, then it's going to be harder than doing an operation with length 1. So, going down the line of trying something of length 1, then you have to do something with the rest of the array, right? So, if you do it on the whole array of length n, that's pointless because you're already doing that. So let's try instead doing some other operation somewhere else. And we have to cover the rest of the array, so we have to cover the remaining n-1 elements. Now this is a good path to go down, because, well, in this construction, first of all, obviously we can do it with the 1. We just subtract 1, and then we have 0. But we can also make it so everything is a multiple of n if we do n-1. Here's the simple way we can do this. Initially, every element is ai, and we can add any multiple of n-1 to this. So let's just add n-1 times ai. Then we get n times ai. ai is an integer, so by definition, this is a multiple of n. There are some ways to come up with something like this. For example, you start with the reverse. You want the numbers to be in the form n times ai, right? So, and currently you have a number ai, and you want to do something to it so it's in the form of n times ai. This is a standard number theory way of representing a number. Or rather, it's not n times ai, actually. Let's say it's n times k. And what we can do is we can add any other element. So we can add ai plus n-1 times x, and we need to make it equal to n times k. So if you just think about it like this, 1 plus n-1 is clearly n. So if we just let x be ai, then times ai, then we'll get a number that's of the form n times k. So thinking about it in terms of like number theory representation, for example, n times some number, then n-1 times some number, it could help you to think about the right things and eventually go down the right path to finding a solution, I guess. With constructive problems, it's always hard to find out how to do this. I just recommend practicing more of them and trying to get down the process of going through ideas in your head if you want to do that, if you want to practice this. So basically the idea is let's say we hijack the first element, we just make it 0, and then to each element we add n-1 times ai. So this we would add plus 9 plus 6 plus 12. Then our resulting array would be 0, 12, 8, 16. And because all of these are multiples of n, in the final operation we can just decrease all of them. So we can do negative 0, because negative 0, negative 12, negative 8, negative 16. And that works quite nicely. I did something very slightly more complicated, but not really that more complicated in my solution. So my code isn't going to exactly match this description, but this is a very easy thing to implement, so I decided to describe this one instead of the one I did. Anyway, that's C. Now we go for D. And D is a game theory problem. However, I solved this problem, and I know almost nothing about how actual game theory works. So what I'm saying is it's not necessarily required to know the ways game theory works, or even have a massive pool of intuition about it. You just have to, you can treat it like a normal problem. You don't have to be scared off by the subject automatically. So here's the problem. You're given a number of piles, much like the classic NIM game. Let's say, for example, you have 3, 1, and 1. There are 2 players. One player goes first, the other player goes second, obviously. And in one move, a player can choose a pile and remove exactly 1 stone from it. Now, the catch is the next player, the player that goes after the other one, can't take a stone from the same pile. They have to choose from a different one. So if the first guy in purple takes a stone from this pile, then the second player can't take a stone from this pile. They have to take it from one of the other ones. So now let's say the purple guy takes a stone from this pile, then both this pile is empty, and the first player can't take a stone from it anyway, so the second player will take a stone from this pile. Now, both of these piles are empty, this pile has 1 stone left, and because the second player just took a stone from this, the first player can't do that. So he has no moves, and he loses. The point of the game is to make it so when a player has no moves, they lose. So you know that both players play optimally, that is, if they have a chance to win. If they have the opportunity to win, they will. They will take the best strategy that they have, and you want to find out who wins. So first we have to figure out the optimal strategy. Let's create an edge case first. Look at this. So the first player can choose this pile. They'll take this pile, then the second player will have to choose some other pile. Then the first player can keep taking things from this pile until the second player runs out of moves. So because the first player goes first, he can essentially dominate the biggest pile and prevent the second player from ever touching it. So if this automatically wins for the first player, then he just wins. And this is only true if the first pile is strictly greater than the sum of stones in all other piles. For example, if we had only one more here, then this wouldn't work out for the first player because he would run out of stones. Even though he kept holding on to this pile and it was the biggest one, he's out of moves now. So the condition for this working is the maximum. This just means the maximum over all I of AI has to be greater than the remaining sum of the remaining elements. Sorry, this is a greater than sign. Okay, that was bad. So the maximum over all AI has to be greater than the sum over all AI, excluding that maximum. Symbolically, this just means the first player will be able to keep taking piles, or keep taking stones from the biggest pile until the first player runs out of moves. Okay, now say this isn't possible. Then now there's the property that, say for example, we have the following piles, 3, 2, and 2. Now, we have the property that consider like the sum of all of the stones in the piles. All AI is not like no pile has more than half of the number of stones. Which means that no matter what, like any player that moves can't do the strategy where they hold on to a pile and exhaust the other player of their moves. Because the other player will have enough moves to outlast this pile, and therefore they'll be able to keep going. So now, in terms of games like this, when both players have the option to play optimally, then one player is going to win. Like the outcome of the game is fixed. So let's say whichever player is going to win, well, they know that they're going to win because they play optimally. So if this condition is maintained throughout the game, then the winning player will always stay in the winning position. And the way the player can maintain this condition is basically by saying, so we'll subtract 1 from like the first player, for example, the first player is going to win here. I just know that. So the first player will subtract from the biggest pile. Then the second player will take from some other pile. Then we have 2, 1, 2. Then the first player will subtract from the biggest pile. Then the second player can subtract from any pile. Now we have 1, 0, 2. Then the first player can subtract from the biggest pile, and the second player will subtract from any pile, and clear the first player wins here, because they take from the 1, and the second player has nothing left to do. So the reason this condition is maintained is because every time the sum goes down by 2. However, every value of AI goes down by at most 1. So that means that, wait, does that work? Actually, I think it's a bit harder to prove than that, but yeah, sorry. It is slightly harder to prove than just doing that, but it's kind of the same basic idea. Like, this sum will go down by 2, which means the requirement for some element to be greater than half, to have greater than half of the number of piles, or greater than half of the number of stones, the requirement goes down by 1 each time. So what that means is that if anything is decreased by, if the biggest elements are decreased by 1 each, then this condition will still be satisfied. And the intuition behind this is that we can't have 2 elements that are bigger than this, because if we did, then those 2 elements would both have to be greater than half the sum, and so the sum can't be that big. So, like, we would have the 2 times AI is greater than the sum itself, which is not possible. Or it would rather be that like AI plus AJ for some different I and J will be greater than the sum over all stones, which obviously can't be true. So there's at most 1 element that will violate the condition at each time, and if that element exists, then the winning player can decrease that element and therefore maintain the condition. That's kind of an informal proof of why that works. So basically, whoever's winning in the start will always stay winning. And the condition for checking if a player is winning in the start is actually just the parity of the number of stones in total. Because since this condition is always maintained, every player will keep taking stones until there are 0 left on the board, or 0 left on all the piles. Since no matter what, one player will keep taking from the maximum, and there's no way that one player can stall out the other player by holding onto a pile. So the game only ends when there are no stones left. So if we consider the process of taking stones, let's say we have 7, then the first player will take a stone, the second player will take a stone, now we have 5. The first player will take a stone, the second player will take a stone. I'll just draw the rest of these out. Then we have 3, then we have 1, now we have 0, and the second player can't make a move, so they lose. So if the number of stones is odd, then the first player wins. Otherwise, then the second player can make this extra move, and then now it's a big switcheroo. The first player doesn't have a move, so he loses. He or she loses. Yeah, so in the code it's the same thing. You basically check if the biggest element is strictly greater than the sum of the rest of them, then the first player automatically wins. Otherwise, it depends only on the parity of the total number of stones. So that is D. Kind of a cool problem. It's also kind of like, I don't know, I don't, like, in contests like these types of problems feel more like guessing, because if you prove it, if you take the time to do a formal proof like this, or even just an intuition-based proof, then you lose, like, a time advantage. Because all points in Codeforces contests are based on time, and if you spend a lot of time developing an elaborate proof, it's going to take a lot of time. So it's comes more down to intuition and kind of just guessing the right thing initially. And it's kind of sad that there are problems like this because it's more about just guessing than actually doing things. Yeah, I guess. So you could either prove it or kind of just go with your gut. If your gut says the right thing, cool. Otherwise, you get it wrong, and then you have to keep figuring it out. And it seems like it kind of adds like an element of luck to these runs. I don't know. I've seen other problems like these. Don't really appreciate them, but at least there is originality in them. At least there is some thinking that it requires. It's kind of like constructive in terms of the solution. So I can see their advantages, but there are also definitely disadvantages to having stuff like this. Yeah, that's what I think. Also, the constraints are small, so if you make the initial observation that you can just keep taking the biggest element each time, then you can actually just simulate the process because it would take O of t n a I, or it would take t n times 100 log n times 100. So it's t times the number of stones. Actually, sorry, just times log n. T times the number of stones you remove times log n because we have n piles to remove each time. And you can do it with like a priority queue or something, or you can even do it in t n squared times 100, whatever works. So that is kind of also a lame solution instead of analytically solving the game. I don't know, all around it felt like this was kind of easy to cheese. So I'm not sure how many people did that. Maybe it would have been easier. Maybe it also, I mean, the 5-line casework isn't that bad itself, but the cheesing solution requires much less thinking. And that's not nice. I think the constraints probably could have been higher for that. But anyway, nothing you can do now. It's my daily dose of complaining about a problem. Now, if you've seen this problem, just look at how much time I spent just scrolling through this statement right now. And I think the statement itself is actually necessary, but like I don't know why they had to bold absolutely everything. Because if you bold everything, it's like nothing is bolded. Like nothing is emphasized because everything is the same, like bold. It just kind of doesn't work out. So describing the game is fine. That feels kind of necessary. Maybe it could have been like less. Maybe it could have been more abstract because like introducing the game concept made the statement incredibly long. So I'm not sure. It also depends on what testers thought about the round, I guess. But this definitely could have been shortened. Okay, anyway, all of that is my daily dose of complaining. We'll get back to the solutions now. Yeah. Let's do E. Problem itself, I did not like it. Well, it's just kind of ugly, like an ugly problem in itself. There is some kind of cool substance to it, like thinking, but it's not amazing. Yeah. So the reason it was ugly is for the solution I'm about to describe right now. There probably is some smoother way where you can use some observation to make it easier. I did try to do that, but in my sleep-deprived state, I wasn't exactly doing so great. So my goal was basically just to solve it, make it work, and be done with it. And that's eventually what I did. So, okay, this is actually a very complex problem. And if I described this statement, it would take longer than the time it took me to explain A, probably. So I will let you read it for yourself. Ask clarifications about it if you don't understand. And now I'll assume you know what the problem is asking. So let's draw out kind of the samples. So we have we're using the first sample, where the cost of using a pistol is 1, the cost of using a laser rifle is 3, and the cost of using the third gun, AWP, is, or OP, AWP, whatever, is 4. And the cost of jumping is 3, or teleporting is 3. So now you have a line of 4 levels. Each level has its own value, and that is, or the number of monsters in each of them. So there are 3, 2, 5, and 1. Now, so in the optimal solution, obviously there's some sort of path. Like for example, you go like this, then go like this, then go like this, then go like this. In this sample, this is the optimal solution that they describe in the sample explanation. And basically here, you fully kill this boss, you fully kill this boss, you damage this boss but don't kill it, and you fully kill this one, then you finally come back and fully kill it. So I actually don't fully understand why this is true, but my solution idea was based on the fact that any optimal strategy can be broken into 2 parts. Some prefix and some suffix. And in the prefix, you do whatever you want, and you solve it independently from the suffix. That is, you can't cross this barrier until you've killed all the bosses in the prefix. And then in the suffix, what you'll do is, basically you'll move in a motion like this, where you go to the end, and you can either kill these bosses or don't, it doesn't matter. Because what we're going to end up doing is trying all possible suffixes. So even if it's optimal to not kill this boss, that means we'll find it later in some other suffix that we solve for. So we're going to assume that we in fact do. We're going to assume that we don't kill every boss in this suffix, except for maybe the last one. The last one is a special case that adds some casework. And basically we assume the path we're going to take is like this. So we go here, we trudge along, we kill all the bosses down to the end, then we go back we don't kill all the bosses. We damage all the bosses but don't fully kill them. Then we reach the end and eventually go back and kill all the bosses in succession until we reach the beginning of the suffix again. That's the path in the suffix. Now there's one extra thing to note about this possible suffix path, that you can, for example, have something like this. So you'll go here, and then, let's say, leave the boss alive, leave all the bosses alive, but then the last boss isn't dead. So even if you go like this, you'll kill all these, but you'll still leave this one alive, and you don't want to do this because this isn't good. So the better thing to do is to go like this, because you're forced to teleport out if you don't kill the last boss. Then go back here, kill the last boss, and then do this motion. So this will cost you 2 extra movements, essentially. But there's another special case. You can't actually hard code in 2 extra movements, because say you only have 2 things in the suffix. Then you'll go here, and then you go here, and then you don't want to go back here and here because you're already done. Like, you've already done these 2. So, yeah, those are some special cases. Have fun with doing those in the code. But essentially, that's what the suffix path is going to look like. You're going to start at the beginning of the suffix, go down to the end, not necessarily kill any of the bosses, then either go like this, or kill the last boss and skip this part. Whichever proves to be more successful. Yeah, so that's how you handle suffixes. And then, so obviously the combined answer is, since you solve the prefix and suffixes independently, it's the cost for the prefix plus the cost for the suffix plus the cost for traversing this edge. And so because the cost of suffixes is predetermined, like in a suffix we can do whatever we want with any boss. In the last boss we handle the special cases as I described before, But here we can do whatever we want. So we basically just do, there are 3 ways to complete a level, or there are 3 ways to get out of a level. Either use the pistol on everything, including the boss. And then that way you'll damage the boss once. Or use the laser on everything, big L. Or use the pistol to kill all the monsters, and then use the AWP, the final gun, to insta-kill the boss. Those are your 3 possibilities. All of those have their own costs. The first, using the pistol that many times, will take in total the cost of using the pistol times AI plus 2. Plus 2 because you end up having to shoot the boss twice no matter what you do. Eventually you have to come back and shoot the boss again. The second case is the pistol plus the cost of using the laser. Since you'll use the laser, and it's also important to note that it's guaranteed that the cost of the pistol is less than or equal to the cost of using the laser, which is less than or equal to the cost of using the AWP. So, so that's fine. Which means that in this case we're going to want to use the laser, then we'll come back and use the pistol to do the final hit point of damage to the boss. And otherwise, if we do this strategy, then it will be the pistol times the number of monsters plus the cost of using the AWP. I actually don't know why I made this M. This should be A, and this should be P times AI plus A. Those are our 3 cases. And for everything in the suffix, we just take the minimum of these. Again, except for the last one, which we'll handle separately. So this is only half of the code, and already there are a ton of special cases, which is why this problem was kind of annoying. But wait, there's more. Now we have to handle the prefix. How do we do that? Since now our path isn't necessarily going to be predetermined. Okay, so now that we know how to compute the suffix, I'm going to delete all of these drawings and essentially assume that we're solving for the prefix for everything. So we're solving as if this whole thing is a prefix. There are many paths we can take here. Okay. So now we have 5 and 1, right? Yeah. Let me get rid of the rest of these. And we'll be off to victory or something. Whatever we want to do in this game. Now we compute a prefix. And basically the idea is we have this magical edge at the end, and we have to be done with all of these bosses before we're allowed to go through this magical edge. So we can do this prefix in I think many ways. One of the ways is doing some observations. The other is dynamic programming, and this is what I did because I'm lazy and I just wanted to get it correct. So the way to do it with dynamic programming is there are 2 states. Let's say you're solving for the prefix up to I. This is convenient because if you're solving for the prefix up to I, like you can basically assume the magical edge is right after, and then the answer, if you solve the prefix up to I, is the DP value here, and then just the suffix value everywhere else. So that's nice to work with. So we have a DP, I'm definitely running out of colors here. We have a DP with 2 states. First, the position, like the number of elements in the prefix we have, and then it's another state, which I'm not exactly sure how to describe. Let me figure out a good name for it. Basically, the state describes that if we're here, we have some unkilled bosses to the left, which means that when we move here, which means that if we move here and we still have some unkilled bosses, eventually we're going to have to go back through this edge and then forward through this edge again. So let's just say unkilled. I don't know. And then this is true if there are unkilled or false if not. So let's say, for example, we leave this boss alive and we kill this boss, and we're solving for this prefix. So now we move on to the next position. However, we still have this unkilled boss over here. And since we have to be done with this whole prefix before we can traverse the magical edge, we're going to have to go back through this. We're going to have to go back through this edge, come back to this boss, and eventually come back here as well. So we traverse each edge going back to the previous one 2 extra times. So we add 2 times 3, or 2 times d in this example, lowercase d. And that's the amount extra we have. So the fact that if we have an unkilled thing and we have to traverse each edge 2 extra times, it means we don't have to keep track of where the unkilled thing is. We only care about if we have one. Because assume we left this boss unkilled. Then when making this transition, we will have already have added the cost for going back through this edge and then going forward through it again. So now, when we're here, we don't care about where this unkilled thing is because we've already taken care of the cost for this being unkilled. So now once we go here, even though this is still unkilled, it's only 1 extra edge that we add because every other edge has already been traversed the 2 extra times. So that makes the transitions much smoother, and it means that we only have to store this much information. So now as for the transitions themselves, they're simple. Either you kill the boss here, and then you do some, like, I don't know, push forward, like feed forward DP, or backwards DP, however you like it. I prefer feed forward because it's easier to work with in terms of things like this, I think. So here, either you kill this boss, in which case you do some casework based on the cost of killing the boss and whether you have unkilled things or not, or you don't kill the boss, in which case you also do casework on the whether you have an unkilled thing or not and the things and the like values. So I'm not going to go over the transitions because there are many of them. I'm very sure I overcomplicated it because you see I have 7 lines of transition, and I think actually most of them aren't necessary. Like, yeah, this is almost kind of the exact same thing, and so is this. So probably many of these transitions could be cut out. And in fact, maybe we can cut out a whole dimension eventually, but it's not necessary. And I think it's good to have this extra dimension so that it just simplifies the code and makes it so you're less likely to make mistakes. That's the way I like to do things. Calm and cautious. So then the value for a prefix is, let's say we have the prefix computed up to here, which means we've solved this whole range. By definition, dp of, for example, 3, 0 indexed, dp of 3 and 0 means that we've killed all the bosses up to this point. So therefore, we're allowed to traverse this magical edge since we're already done. And then we just take the value of the suffix, whatever magic goes on beyond this red edge. This is a 3, by the way, poorly drawn, but that makes it worse. Yeah, handwriting's still not getting better. So that's how it works. If you've made it this far and you understand everything I said, probably you can work out the transitions by yourself. So have fun with that. And the final answer is the minimum over all I of dp I 0, and then a special suffix value for computing the suffix, like computing the cost of like Remember at the beginning we computed the cost for doing a suffix, that is doing some path that possibly looks like this. Or we just remove this part and we go like this. And because this is the end, we're done, so we don't have to end up taking this extra edge back. That's what a suffix is like. So we can pre-compute the answer for all of those suffixes in O of n. We can do this dp in O of n, although it's kind of a terrible complexity for mine, or a terrible constant, because I have 7 transitions, so it's more like, kind of behaves like n log n, but not exactly. But anyway, it's O of n in total. And of course, if there's no suffix, that is, if we're accessing like suffix n, which doesn't exist in zero indexing, just don't use it. So be careful with that. And yeah, so there are 2 n states. Each state has kind of O of 1 transitions. And there are n suffixes. So in total, the solution is O of n. Anyway, that's it. That's E. So these were all the div2 solutions. In the like timestamps, I'll also index them in terms of div1. So if you came from div1 and you're interested in some solutions, you can watch it. You can see how they are relative to div1 as well. Yeah, that is all. I hope you enjoy what I have in store for the future. Let's see, have we gotten to 1,000? I don't think we have, but we're incredibly close. 996. Yeah, so hopefully we'll be able to get there soon. Very, very soon. And I don't know what I'll do. I guess we can do our first virtual live stream in honor of reaching 1,000 subscribers. That should be fun. Oh, and also, even though I didn't have the opportunity to do this before the contest, I'm going to do this now and put this in my template. And that's it. See you guys.